start here. We ended last class talking about how to carry on uncertainty in a calculation. Why we do that is because if each measurement has uncertainty and we're using those calculations to calculate something else, the result of the calculation has to have uncertainty as well, right? It would make sense. And what happens is, since both of them are uncertain to a point, to a certain degree, the uncertainty is always going to increase when you're using more than one measurement for a calculation where both of them have uncertainty. Does that make sense, guys? You can never have less uncertainty when the things you're using have uncertainty. So when we're adding and subtracting measured values, so say a student is trying to calculate the mass of copper, and we're going to be doing something very similar to this soon. So a student measures the beaker in the copper to be 123.4 plus or minus 0.1 grams. The student measures the mass of the beaker previous to that, and that is 113.8 plus or minus 0.1 grams. So the mass of copper is pretty easy to calculate. It's 9.6. What do you guys think the uncertainty is? I want you guys to work together and figure it out for a second. Just talk to each other. So when we're calculating the mass of the copper, the uncertainty has to increase. So when we're adding and subtracting, the uncertainty is just added. That's it. We add the absolute uncertainties. So my overall mass of my copper is going to be 9.6 plus or minus 0.2. The 0.2 comes from adding the absolute uncertainties. Right? And it makes sense when we think about it in terms of units, doesn't it? If I'm adding grams and grams, right, I can just add them. Right? If I have, or subtract them. If I'm subtracting grams, I can add and subtract those because they're like units. Right? If I had grams and milliliters, could I subtract grams from milliliters? No, that doesn't make sense. Okay? So our mass of copper here is 9.6 plus or minus 0.2. So did we try one of these examples yet, guys? Okay. All right. So let's move through these. So these operations we're adding, as you can see. So all we have to do is add the uncertainties to get 0.2 plus 0.1 plus 0.3 to get 0.6. Even when you're subtracting, you're adding the uncertainty. So 0.2 plus 0.2 is 0.4. All right, and we'll move on. And I think maybe we got to this point. I think I'm confusing my classes. So when we're multiplying or dividing measured values, so like, say we're calculating the ratio of distance and time. Both in your measuring your time, that has uncertainty, and your distance also has uncertainty. So what we have to do is we have to add the percent uncertainty. So the percent uncertainty is just the percent the uncertainty is of the numerical value of your measurement or your calculation. So let's say, talked about the copper. Let's say the mass of the copper is 9.6 plus or minus 0.2. Our percent uncertainty is just going to be the uncertainty divided by the measurement times 100%. Okay? Do you guys see where that came from? The 0.2 is the uncertainty. The 9.6 is the measurement. So it's what percent the uncertainty is of the measurement. So if you take 0.2 divided by 9.6 times 100%, round to 1 sig fig, you get 2%. It's got to be like, what, 1.8 something? You want to round that to 1 sig fig. We'll get practice with this later. Okay? So my mass of copper is 9.6 plus or minus 2%. Okay, the uncertainty is 2% of the measurement. Okay, so when we're I want you guys to try one of these. Just find the percent uncertainty for the first value. All right. So if you want, you guys can take a look at these later if you want some more practice. So what we should have got is 13.1 plus or minus 5%. That's because 0.6 is 5% of 13.1. Make sense? So it's just converting into percents. Because why we do that is because we can, it's the same unit. We're talking about percents. And you'll see why in a sec. So moving forward, when we're multiplying and dividing, we want to add our percent uncertainty. So that's our other move on. So for instance, if I have 22.2 centimeters plus or minus 2%, I'm multiplying by 45.2 centimeters plus or minus 5%. I want to get, so why don't you guys try that first one there? Work as a group quickly. See what you guys come up with. So let's move on. So I actually need to put in a line right there, but that's okay. Experimental error. You know what? Let's talk about this real quick. When you're talking accuracy, and there's the terms accuracy and precision are oftentimes confused. Okay, so they are different. Accuracy is how close you are to an accepted value. That's when you're referring to accuracy. Precision is the degree of certainty of a measurement or a calculation. Okay? So if I'm very accurate, I'm very close to the accepted value. If I'm very precise, I have a low uncertainty. Or I have a high degree of certainty. Okay? So the lower my uncertainty, the more precise something is. Does that make sense, guys? So don't get confused. A lot of times people throw these terms around, accuracy and precision, without actually using them correctly. Okay? So I like to do the dartboard because A is very precise, but it's not accurate because it's not close to your target value. B is more accurate because the groupings are close to your target value, but the measurements are high. They have a high uncertainty. They're all over the place. They're farther away from the target. So you can have high accuracy and low precision. Excuse me, high precision and low accuracy. You can also have low precision and high accuracy. It's just important to determine it correctly. Experimental error, and this is what we're going to talk more about in our density lab. Is there's two types of error, and this is about the experiment. There's limitations to every experiment. So there's systemic errors, which are always involved in your lab because of the procedure. They are, no matter what you do in that procedure, this type of error will be present. Okay? So that's what they mean by systemic. If you repeated the experiment 100 times, this type of error would always be there. So they can be associated with the precision of the device used to measure. So for instance, uncertainty is something that is going to be a type of systemic error that is always involved when you're doing measurements. So if you're measuring, if you're using a balance in the lab, uncertainty is going to be systemic error all the time because that balance has uncertainty. It has a limitation to how much it can measure, to the degree of certainty. Okay? I'll post this right after this, guys, so you guys don't worry about getting it all down now. You can finish this up later. Random errors or non-systemic errors are just, they're just not necessarily going to be repeated. They're just random things that happen in your lab. Say, for instance, you are measuring the mass of copper 2 oxide, and then a fly lands in your balance. The fly adds mass. That's not necessarily going to occur every single time, unless you have a lot of flies in your lab. Just kidding. So that's not necessarily going to happen again. Or if you do something wrong that you're not supposed to do, that wouldn't necessarily be repeated again in the lab. Okay? So they tend to be more random or non-systemic. They're not built in the system. Okay? Makes sense? And and basically what scientists do is we try to minimize these. You try to get your systemic error as low as possible, and your random error, your non-systemic error, as low as possible as well. So that hopefully will lead to give you the best results and the most accurate results. So they are related. Okay? Makes sense? We're done.